What if something passed through our solar system that did not belong here, and we only realized how strange it was after it was already on its way out? Interstellar objects are not new to astronomy, at least not anymore. We have seen them before. Brief visitors moving fast, quiet, indifferent to the sun's pull. Most of the time, they are curiosities, data points, a chance to study material formed around another star. But 3I Atlas did not stay a curiosity for long. At first glance, it looked ordinary. A faint object detected by an automated sky survey, moving too fast to be bound to the sun. The kind of discovery astronomers are trained to expect, document, and move on from. And yet, within weeks, the language around it changed. Cautious statements replaced confident classifications. Public data thinned out. Questions began to outnumber answers. Why did attention escalate so quickly? Why did an object described as a simple interstellar comet trigger such careful restraint? Why did the discussion shift from open excitement to measured silence? What the public saw were grainy images, light curves, and careful phrasing. What we did not see was just as important: fewer updates, fewer interpretations, fewer conclusions. This is not a story about hidden truths or secret knowledge. It is a story about uncertainty, and how institutions respond when observations refuse to fit clean categories. Tonight, we are not here to decide what 3I Atlas is. We are here to understand why it unsettled expectations, why a visitor from another star system raised questions that remain unanswered, and why this quiet object drifting through the dark may be forcing us to confront how little we truly understand about what moves between the stars. The discovery of 3I Atlas began the way many modern astronomical discoveries do, without drama, without intention, and without a human eye at the telescope. The Atlas survey system scans the sky every clear night, searching for objects that move against the fixed background of stars. Its job is simple: detect motion, flag anything that does not behave as expected. Most of what it finds are ordinary asteroids. Some are comets. A few are near-Earth objects worth tracking more closely. In July 2025, Atlas flagged something different. The object was moving fast, too fast. Its trajectory did not curve the way solar system bodies do. Initial calculations showed a hyperbolic path, meaning it was not orbiting the sun. It had entered the solar system from interstellar space and would leave the same way, never to return. That single calculation changed everything. An object on a hyperbolic trajectory is not native to our solar system. It belongs to another star system entirely. That immediately placed 3I Atlas in an extremely rare category. Only 2 such objects had ever been confirmed before. Follow-up observations began almost immediately. Telescopes around the world tracked its motion, refining measurements of its speed, brightness, and direction of approach. Radio observatories and deep space tracking networks contributed data to better understand its velocity and physical properties. What scientists saw confirmed the initial assessment. 3I Atlas was moving at interstellar speed, far beyond what gravity alone could produce within the solar system. Its path traced a clean entry and exit, untouched by long-term solar influence. For astronomers, this was a once-in-a-lifetime opportunity. Interstellar objects carry information from beyond our stellar neighborhood. Their composition reflects the chemistry of other star systems. Their structure offers clues about how planets and debris form elsewhere in the galaxy. Excitement was real, but it was cautious. Every measurement mattered. Every assumption was checked twice. Unlike asteroids or comets we see regularly, there would be no second chance to study this object. And yet, even in these early days, something felt different. As data accumulated, classification became harder, not easier. 3I Atlas fit the definition of an interstellar object perfectly, but its physical behavior did not settle into familiar patterns. The discovery opened a door. But instead of clarity, it revealed a deeper set of questions that would only grow louder as more observations came in. To understand why 3I Atlas became puzzling, we need to understand what scientists expected to see. When astronomers observe small bodies in space, they rely on several key tools. Spectroscopy breaks incoming light into its component wavelengths, revealing which elements and compounds are present. Light curves track changes in brightness over time, offering clues about shape, rotation, and activity. Motion analysis reveals how forces like gravity and outgassing influence trajectory. For interstellar objects, expectations are grounded in comets. A typical comet contains volatile ices. As it approaches the sun, those ices heat up and sublimate, releasing gas and dust. This creates a coma and often a visible tail. Brightness increases predictably. Small forces from outgassing cause subtle but measurable changes in motion. 3I Atlas did not follow this script cleanly. Spectral data showed fewer strong signatures of common cometary gases than expected. Some emissions appeared weak or inconsistent with its distance from the sun. Its brightness varied, but not in ways that matched standard models of sublimation. This did not mean something impossible was happening. It meant models did not fit neatly. Light curve analysis suggested either an unusual surface structure or a composition that suppressed normal outgassing. A thick insulating crust could trap volatile volatiles beneath the surface. Exotic ice mixtures could behave differently under solar heating. Both explanations remain physically plausible. Trajectory analysis added another layer of complexity. Small deviations in motion are normal for comets caused by jets of gas acting like tiny thrusters. But when dealing with an object moving at interstellar speed, even small deviations attract attention. In the case of 3I Atlas, motion remained largely consistent with gravitational expectations, but subtle irregularities resisted clean interpretation. Not dramatic enough to claim anomaly, not simple enough to ignore. Scientists faced a familiar but uncomfortable position. The data did not point to a clear answer. Classification remained tentative. Language became careful. This is how science often feels in real time. Not decisive, not cinematic, just unresolved. The object was clearly interstellar. That much was certain. But whether it was a comet behaving strangely or something rarer still remained an open question. And that uncertainty, rather than any single measurement, is what gave 3I Atlas its weight. Because when an object refuses to fit, it forces us to ask whether the categories themselves are incomplete. When data resists simple classification, theories multiply. The most conservative explanation for 3I Atlas is also the most likely. It is a natural object, a comet or asteroid formed around another star, carrying unusual properties shaped by a different environment. Interstellar space is harsh. Over millions or billions of years, cosmic radiation can alter surfaces. Volatile materials can be depleted. Crusts can form that suppress activity. A body like this could appear inactive or inconsistent until heated deeply enough to break through its surface layers. Another possibility involves composition. Not all ice is the same. Mixtures of carbon monoxide, carbon dioxide, or nitrogen ice behave differently than water ice. These materials sublimate at different temperatures and pressures, producing unfamiliar patterns of activity. All of these explanations fit within known physics. They do not require new forces or unknown mechanisms. They simply require conditions we have not observed often. Only after these natural explanations are considered does speculation move further out. Some researchers have asked, cautiously and hypothetically, whether some interstellar objects could be artificial. Not as a claim, but as a boundary test. If humanity were to send probes between stars, what would they look like? How would they move? How would we detect them? This line of thinking is not new. It exists at the edges of scientific discussion, often as a way to examine assumptions rather than assert conclusions. In the case of 3I Atlas, no evidence supports an artificial origin. No signals, no structures, no behavior that clearly violates natural explanations. The anomalies are subtle, not definitive, and that distinction matters. Extraordinary claims require extraordinary evidence. So far, the evidence points only to uncertainty, not revelation. What makes 3I Atlas compelling is not that it suggests an answer, but that it exposes how limited our sample size truly is. We have seen too few interstellar objects to define what normal even means. Both natural and speculative theories leave us with the same truth. We do not yet know enough, and sometimes mystery is not a sign of something hidden, but a reminder of how much remains unexplored. As 3I Atlas continues its journey through the solar system, one event stands out as especially important. In March 2026, the object will pass near Jupiter. Close encounters with massive planets are valuable. Jupiter's immense gravity can subtly alter an object's trajectory, allowing scientists to refine measurements with greater precision. Changes in brightness, activity, or motion become easier to detect against strong gravitational influence. Scientists will be watching carefully. If 3I Atlas behaves like a typical comet, increased solar and tidal effects may trigger new activity. Jets could emerge, emissions could strengthen, motion could show clearer non-gravitational forces. If it remains quiet, that silence itself becomes data. Trajectory predictions will also be tested. Even small deviations could help constrain models of mass, structure, and composition, not as proof of anomaly, but as refinement of understanding. Importantly, no single observation will provide final answers. Science rarely works that way. Instead, the Jupiter flyby represents one more piece of a growing puzzle. What matters most is consistency. Does the object behave in ways that align with natural explanations as conditions change, or does uncertainty persist? Either outcome teaches us something. The flyby is not a moment of revelation, it is a moment of measurement. And in that quiet accumulation of data, clarity may begin to emerge, slowly, patiently, as it always does in science. 3I Atlas is real, it is interstellar, and it is scientifically valuable. Its behavior has challenged expectations, not by defying physics, but by refusing easy classification. Spectral data raised questions. Activity patterns resisted familiar models. Motion analysis demanded caution rather than certainty. We explored natural explanations grounded in known science. We examined speculative ideas carefully. Without granting them weight, they have not earned. And we looked ahead to future observations that may, over time, narrow the possibilities.
What remains is not an answer, but a reminder. Interstellar objects are messengers from beyond our solar system, even if their message is simply that the universe is more diverse than our models assume. Each one expands our understanding, not by confirming what we know, but by revealing what we do not. 3i Atlas does not need to be extraordinary to matter. Its significance lies in how it exposes the edges of our knowledge. As we continue to observe, measure, and refine, this object will either settle into familiarity or remain an outlier that reshapes our expectations. And perhaps that is the deeper question. What if this is only the beginning? What if interstellar visitors are far more common than we once believed? And what if each one carries a lesson about the vast, quiet complexity of the universe we are only beginning to explore? Until then, the mystery remains open, where it belongs. Keep looking up.